we take a brief break from our perusal of resonance structures to explore the concept of electronegativity, which is going to become important as we finish the topic of resonance structures. So up until now, we've assumed that the two atoms participating in a covalent bond share the pair of electrons equally. In reality, some elements want electrons more than others do. Elements don't play completely fair. So we've already met in the context of atoms the concept of electron affinity, which is a measure of how much an isolated gas phase atom wants to gain an electron and form an anion. Electronegativity is a measure of how much an atom participating in a covalent bond wants to pull electron density towards itself. Okay, so electron affinity is defined for individual atoms. Electronegativity is a somewhat similar concept, but it's only defined for atoms in molecules. So the first electronegativity scale was proposed by a chemist named Linus Pauling in 1932. And I want to take a minute and just tell you a few interesting facts about Linus Pauling, because he's someone you should know something a little more about. Pauling was one of the first important American chemists. So here's his picture down on the bottom right. So he was a professor at Caltech for almost 40 years. He wrote a book in 1939 called The Nature of the Chemical Bond, and it's one of the most important chemistry books ever written. And I still remember when I was a high school student checking this book out of my high school library and attempting to get through it, although I didn't really quite know enough chemistry as a high school student to make sense of it yet. Pauling won the Nobel Prize in Chemistry in 1954 for his research into the nature of the chemical bond and its application to the elucidation of the structure of complex substances. So Pauling did come up with theories, but he was also an experimentalist, working in an area known as X-ray crystallography, which is how you actually determine the three-dimensional structures of molecules. And then if that wasn't enough, Pauling won the Nobel Peace Prize 8 years later in 1962 for his very, very well-developed opposition to weapons of mass destruction, which at that time were nuclear bombs. Pauling is actually the only person ever to win 2 unshared Nobel Prizes. Okay, so what did Pauling do in the context of electronegativity? Well, he came up with a scale, and these numbers, these electronegativity values, are still today called their Pauling electronegativities. So Pauling defined fluorine, which is the most electronegative element, to have a value of 4.0. And then he assigned every other element to have a value relative to fluorine. So how much electronegativity does it have compared to fluorine being a 4? So the elements range from 0.7 for the least electronegative elements to 4.0. So electronegativity is also a periodic trend, and it tracks with electron affinity and ionization energy. Okay, so in general, electronegativity increases as you go to the right across a period or up a group. Now you'll see this isn't perfect, so thallium actually has a higher electronegativity than indium does. Germanium is higher than silicon, but they're pretty close. So what you should be able to glean from this picture of the periodic table is that all of the nonmetals have electronegativities greater than 2, and most of the metals are less than 2. There are a few of the transition metals that actually do have electronegativities greater than 2. But there are only 5 elements that actually have electronegativities greater than 3. And they are nitrogen, oxygen, fluorine, chlorine, and bromine. And then what you should also note here is the roughly diagonal relationship between elements with similar electronegativities. So, for example, oxygen and chlorine are pretty close, and you can draw a diagonal line that connects them. Nitrogen and bromine are both 3.0, they can be connected with a diagonal line. Yes, that one goes through sulfur that's less electronegative, but this is to a first approximation. Then everything with very low electronegativities are the metals on the left side of the periodic table. So sodium, potassium, rubidium, strontium, cesium, barium, all of those have electronegativities of less than 1. Okay, so why do we care about this? Well, the first thing is we can make some generalizations about bonding now using electronegativity in our argument. So we previously said that ionic bonds occur between metals and nonmetals. But the more precise definition is that ionic bonds occur where there is a large electronegativity difference between the two partners. So in this case, the more electronegative element essentially takes both of the bonding electrons from the less electronegative element. We said that covalent bonds occur between nonmetals, which is generally true. But the more precise definition again here is that covalent bonds occur when there is a small electronegativity difference between the two partners, but a large average electronegativity. So in case you're curious, when there is a small electronegativity difference between the partners and a small average electronegativity, then you have metallic bonding. So you either have a pure elemental metal or an alloy that is a mixture of metals. But what metallic bonding means is that all of the nuclei are fixed in space in a crystal lattice, and then the electrons are actually free to move wherever they want through the lattice. And this is sometimes called the sea of electrons. Okay, so we also had a lesson in a previous unit where we started talking about oxidation reduction reactions, and we defined oxidation states. We defined it pretty precisely for metals, but weren't able to, at that point, come up with a precise definition for nonmetals. We just kind of said the higher oxidation state was the more bonds to things, kind of up and to the right on the periodic table. Well, to more precisely define the oxidation state for a nonmetal, the oxidation state is the number of bonds to a more electronegative element minus the number of bonds to a less electronegative element. Okay, so as an example, if we wanted to figure out the oxidation state for carbon in dichloromethane, CH2Cl2, we would come up with the conclusion that that oxidation state is in fact 0. Because that carbon is forming 2 bonds to chlorine, which is a more electronegative element, and 2 bonds to hydrogen, which is a less electronegative element. So the +2 and the -2 cancel each other out, and that gives us 0. So there will be 2 more applications of electronegativity in this unit, which is why we are bringing it up right now. So the first application is going to be to major resonance structures, and that's going to be in the next lesson, which is why I actually put this lesson on electronegativity right in the middle of our lesson on resonance. And then the second application is on the topic of polar covalent bonds, which will come up in a couple of lessons. So that is when the electronegativity difference between elements participating in a covalent bond is greater than 0.5, which is still relatively small, but non-zero. Okay, so now in our next lesson, we will finish up the topic of resonance structures, including our argument on electronegativity.